Hello everyone, let's move this a bit. Alrighty, so how are you guys doing? Hopefully the air is pretty good so far in Ridge, because hopefully no one else is like dying from particulates in the air. So yeah, we are ready to continue our next. Hold on. Let's get rid of that. Okay. We are going to continue today learning about electron structure. Which is going to be something that you guys will hate. But we got to do it. So, sorry. This one is probably like the most conceptual of all the chapters. And it's, again, something that's not going to be as intuitive. But you will see there is definitely a method to the madness here. And the stuff that we learn will be kind of the reasons why a lot of different atoms will behave the way they will. So we are going to start delving into that. So, but first things first, we want to first talk about light. And let's see. This is chapter 4, by the way, in the textbook. Or it's going to be, I think, chapter 9 if you're using Tro's textbook. Tro, again, does a little bit of a different order of topics, but it's okay. It'll still have the same information. Okay, so let's talk about light. So, first thing we want to know is that light occurs as waves, right? So light, will look like a wave. It's technically got two parts. It's got an electric component and a magnetic component. And so these are often called electromagnetic waves or electromagnetic radiation. Again, that's the same thing as light. Of course, as chemists and scientists, we just have to have fancy names for everything. So technically, this is called electromagnetic radiation, and we're going to learn a lot about it. So, but let's first look at waves here. So, looking at this wave, there are going to be a few properties that we're going to be able to use to describe any wave that you have. Of course, if you take physics, you'll be doing this in a lot more detail, but we do need some basic terminology here when we're talking about waves. So the first one is what's called the wavelength, which is abbreviated with the Greek letter lambda there. That's that kind of squiggly dude in the front. The wavelength describes how far distance it is between two peaks of the waves. So waves, of course, oscillate. They just go up and down, up and down, up and down in the kind of same pattern over and over and over. Let's see. So I'm hearing my computer fan just go berserk right now, but hopefully that's not too loud. I can keep yelling. That'll maybe overcome some of that. So since waves are just repeating over and over and over forever, we can talk about these wavelengths because they're going to be the same for every particular wave of light. So wavelength does not change as you go. So if you're looking at a light beam coming out of the sun versus when it comes on Earth, the wavelength isn't really going to change unless we have some fun stuff happening. Alrighty, we also have another property called the amplitude. And that is basically the distance between when the wave is at its lowest point and it's at its highest point. In sound waves, the amplitude is related to how loud the sound is. And that's the same idea here, is the amplitude is going to be kind of how intense your light beam is. So just another property there. And then one that's not as visible to us when we're talking about waves like this directly is what's called the frequency, which is this Greek letter nu. It's not a V, it's a fancy V. It's a kind of squiggly V. That's a Greek letter nu. Frequency is basically how long, or rather how many times a wave will go through its wavelength in a certain amount of time. So that's just how quickly it's going up and down. So if we're comparing some waves, let's see if I can duplicate this. If we're looking at these two waves, I'm just going to pretend the amplitudes are the same, just because that's the hardest one to duplicate. We see these two waves have different wavelengths, right? Different wavelengths. So the distance between the two highest points here would be one wavelength. And the distance here would also be a wavelength. You could also measure the two lowest points. They should be the same as well. Or like the middle point. As long as you're choosing the same point on the wave, your wavelength will be the same. So looking at these, we can see this one has a longer wavelength, right? We can see visibly there that that wave is more spread out. It's going to have a longer distance between its two kind of peaks there. Alrighty, and so if we imagine, okay, if these waves are both traveling at the same speed, the speed of light, we're going to imagine that it's going to be a lot faster for this wave on the bottom to kind of reach those midpoints, or those highest points, right? Since these waves are both moving at the same time, if the second wave there has a shorter distance to go, it's going to be moving faster, or it's going to seem faster, right? Just to get through those wavelengths. And so we're going to say that this has a higher frequency, right? Just how often it's hitting those peaks. This one with a shorter wavelength will have the higher frequency. Just because since they're moving at the same speed, we're going to hit more of those kind of peaks in the same amount of time. And therefore, we can have a relationship between frequency and wavelength, right? We see that if you have a longer wavelength, you're going to have a shorter or a smaller frequency. Not short. Let's say a small frequency. Alrighty, and if you are a shorter wavelength, you have a higher frequency. Alrighty, again, because all light waves are going to be traveling at the speed of light. So since they're traveling at the same speed, shorter wavelength means higher frequency. Alrighty, so you will be expected to kind of understand that relationship. So comparing wavelengths of different frequencies or wavelengths, you should be able to tell me other things about them. Amplitude is not something we're going to have a direct relationship for in this course, so we're not really going to worry about amplitude too much for right now, at least. Okie dokie. Any questions on that so far? So, in that case, let's move on. We're going to see that we have a way of kind of classifying different waves of light. And so, we can either classify them as wavelength or frequency. For me, I think I prefer to do it as wavelength. But we can do the same thing. And let's go ahead and start kind of in the middle-ish here. This area is going to be where we have visible light. This is the light that we can see. Just so you know, in terms of wavelength, this goes from about 400 nanometers to about 700 nanometers. So pretty strong, right? Nano is 10 to the minus 9. So these are our short wavelengths, right? So we're going to remember that we have a happy rainbow, right? That we have learned in elementary school, or we've seen one or whatever. Let's see. Blue. And then purple. Cool. It is nice being able to have all of these things, all of these fancy colors on my tablet for you guys. So we're going to see that the visible light spectrum, which runs between 400 to 700 nanometers in wavelength, is going to kind of follow the order of the rainbow here. So at the higher wavelength end, we are going to see that that's going to be our red. So in a rainbow, that's the outside, right? We're going to have red, orange, yellow, green, blue, and then violet, or purple, whichever way you talk about it. And then if you go from short wavelength, it's the opposite direction. So the shortest wavelength is going to be purple, and you're going to keep going longer and longer as you get to red. So the opposite, from the inside to the outside of your rainbow there. So I would also expect you to be able to tell me, if I ask you to compare green light and orange light, for example, if you could tell me which one has the shorter wavelength or the higher frequency or whatever, we can talk about that as well. So you'll be expected to go on that end. So we have other parts of the spectrum here that kind of flank the visible light region. And you've probably heard about these. Here we have the infrared region, which is going to be longer wavelength than red. And over here we have ultraviolet, UV. And those wavelengths are going to go basically kind of just kind of on the opposite sides of the visible light here. So infrared just past the red, and ultraviolet will be just past the purple. So we're going to see that we have other ones on either side. Up past the infrared is going to be where we have microwaves. Those are typically on the scale of micrometers, hence microwaves. And then longer than microwaves are going to be what are called radio waves. And those are going to be millimeters to meters to kilometers. So yeah, you can have wavelengths that are kilometers long, as in, you would have to drive, or I guess we could be, exercise conscious. If you were to do a 5K or something, you would hit 5 wavelengths. That's a really long light wave, right? Going the other way, past our ultraviolet region, we're going to have X-rays and gamma rays. And so kind of at this point, we're going down into the picometer range as we go into X-rays and gamma rays. And so we're going to see that we have these really short wavelengths coming together. And so you've probably, learned it in real life that, ultraviolet light is not great for us, right? We'll get sunburned, we'll get skin cancer, we'll have a lot of problems, not the greatest things. And if you're standing in the X-ray chamber all the time, that's also not a good thing, right? Of course, when you go to the dentist or to the doctor or whatever, and you are getting something X-rayed, they're going to be putting, various protective gear on you to, isolate just the one part they want to put the X-rays on, because X-rays are pretty harmful too, right? Down here is what's called ionizing radiation. This is high enough energy to displace electrons. So electrons, as we know, orbiting the atom, kind of having fun, zipping around the atom. These waves of light, these X-rays and gamma rays, and sometimes your UV, can be high enough to kick out electrons. That's why solar panels are designed to absorb UV light, something that has high enough energy to kick electrons out. And when those do, those electrons can flow around and create electricity for us. So we're going to see that we have this ionizing radiation towards the short wavelength end. And so, that being said, we're going to have another relationship here. We're going to have the short wavelength is going to be high energy. And we actually have a fun equation for this. Energy is going to be a couple of constants. H and C are both constants, mathematical constants. And we're going to have the wavelength on the bottom. So, let me just write that out. If you really want to know what these are, that's 6.626 times 10 to the negative 34 joules times seconds. And then C is speed of light. Actually, I think it's 3.01. You're not going to need these. We're not going to do a calculation in this course for the energy or relationship to wavelength. However, I want you to understand that, as wavelength goes down, the energy goes up, right? Because it's in the denominator. So, as your wavelength goes down, the smaller your wavelength gets. Remember, if you're in the denominator, the smaller you get, the bigger your answer is going to be, right? So your energy is going to go up as your wavelength goes down. So I could ask you to compare two wavelengths of light and ask you to tell me which one has higher energy. I could also ask you to, for example, let me throw one more equation at you, because we love equations. Energy is also related to frequency. And so we can see here in this equation, as frequency goes up, the energy goes up. So, since we learned that the wavelength and the frequency are kind of the opposite, right? No calculations for this one, yeah. I mean, that's just stuff you'll do in 111. So if you end up having to do that. So right now, this one's not going to have any calculations for us. But again, understanding here these two relationships. So this one is an inverse relationship, right? And this one is a direct relationship. By the way, if you couldn't tell, just from these equations, frequency is technically, I'll just give that to you. Hooray! Frequency is related to the speed of light over the wavelength. Just if you couldn't tell from those equations as it is. So Maya, that's always the case depending on the internet situation. So if it's being pretty bad with buffering, we might just have to have you watch the videos later or something. Okay, cool. So let's see what we can do with this information. So remember, low wavelength, small wavelength, short, high energy. All right, big frequency, very high frequency means high energy. Alrighty, so let's do it. Let's compare two wavelengths of light. Okay, that sounds good, Maya. Yep, sorry, internet is our enemy. Alrighty, so if we were to compare these two wavelengths, let's talk about which one has higher energy. And let's see which one has a higher frequency. Which one do we think it's going to be? So we have two different wavelengths here. Remember, wavelengths are distances, so that's going to be measured in meters or some derivation thereof. And energy, of course, is in joules. Frequency is in what's called hertz, which is inverse seconds. How many times per second? What do we think here? Which one of those two is going to be the higher energy wavelength? Any ideas? Yeah, right. So this one is the shorter wavelength, right? So that should be higher energy and higher frequency than the other one. So with this, I mean, it's a pretty simple relationship here. So as long as you understand short wavelength means high frequency means high energy, that's kind of what we're going for here. The only way I could make this more difficult would be, for example, to say I have something of I could maybe throw it in different units. That's pretty much the only thing I could do to make this more challenging. If you were to look at something like this, you would just want to get them into the same unit. And so, you know, if we put them in meters, that's probably the easiest way to go to compare which one has higher energy. And so what we'll want to do is put them in the same unit. So a lot of students, actually I think it was more in 111 that we got this question, but there was a question about like if exams are cumulative or not, and I mean, well, I'm probably not going to be asking you to do empirical formula again until the final exam or something. Some of this stuff will be kind of continuous throughout. So dimensional analysis or unit conversions is always a big thing in chemistry. So, you know, you're not done with that. However, there are other aspects which we are done on, at least until the final exam. So you can just, you know, empty them from your brain for now. Okay, so looking at that, we can put this into, you know, since these are both base meters, that's probably the easiest one. We could convert them both to centimeters or both to micrometers, does not matter. Or you could put them in kilometers for some reason, but as long as they're the same unit, that's what matters. So let's put them in meters. I think that's the easiest way to go around. So hopefully remember our metric conversions here. Remember, we're going to want to put cm on the bottom, meters on top. And if we remember our happy chart that's in Discord for us, remember that there's that 10 to the minus 2 meters is the same as 1 centimeter. And so that's going to be 1.62 times 10 to the negative 8 meters. Okay, nothing new, just unit conversion. The other one, 8.12 times 10 to the negative 4 micrometers. Remember, a micrometer is 10 to the negative 6 meters. And so, thankfully, I can do these in my head because these are just exponents. I can thankfully add things in my head. Looking at those two, we see that this one on the bottom is the shorter wavelength, right? Exponents, remember, because that number 10 to the minus 10 is smaller than 10 to the minus 8, that means this one down here has the shorter wavelength, this one is the longer wavelength. And remember always that the shorter wavelength means high energy or high frequency. Okay, so our answer would technically be this second one down here, the one that was in micrometers to start with. Okay, so again, the only way I could make that more difficult from that relationship is to throw in different units. Again, that's the only thing I can do. So don't forget your unit conversions. Don't forget your metric stuff. If you are going to take C11 111 in the future, you'll need all this same metric stuff anyway, so it's a good idea to keep it in your brains. Alrighty, any questions on that one before we continue talking about light? Alrighty. So let's see what happens when light waves mess with each other. I'm going to try and draw two light waves together. Let's pretend those are like identical, okay, because my drawing sucks. If the wavelengths are the same, because again my drawing sucks, but let's pretend they are. And if the peaks align with each other, as in at the same time they're going in their like highest point. So when the first wave is at its highest point, the second wave is also at its highest point. That's what I mean by they're aligned, they're together. We call this in phase. So when waves are in phase with each other, they have the same wavelength and they are at the same kind of point in their oscillation as each other at the same time. So when first wavelength is at its bottom point, the second wavelength is also at its bottom point. And since they're moving again at the same speed, they are in phase with each other. So anything else let me rephrase that. If they have the same wavelengths but not aligned, that's going to be out of phase. And so what that might look like would be something like this, where, okay, this particular wave, again, we're going to pretend the same wavelength here. Well, what that first one is kind of at its peak area. The second one is not at its highest point. It's somewhere else. So this second one is going to be, in this case, is actually quite low, where it happens to be. So these wavelengths are out of phase, whereas the ones, not wavelengths, waves, these ones upstairs, up on the top, were in phase. If they are not aligned, they are out of phase. And so waves actually can interfere with each other. And so if we have in-phase waves, okay, let's see. Again, my drawings suck, but let's pretend those are in phase. How those actually end up working is they will kind of combine together to, let me redraw that because that was really awful. Okay. Okay. Again, I'm sorry, my horrible drawings just look like I'm just drawing squiggles, which I kind of am. Some things to look at. So we remember each wavelength had its kind of, not wave, each wave had its own amplitude and its own, wavelength, right? What we're going to see is these will do what's called constructive interference. Is that if two waves are in phase with each other, and they're kind of going, right next to each other or on top of each other, they will actually combine to make a bigger wave. Notice that now, I'm sorry, I'm going to have to draw it on this side. That amplitude of the combined wave is just the sum of the other two waves that made it up. So we're essentially just kind of adding these two waves together. And so we're going to see that this has to do with the kind of intensity of light. So we saw previously that the wavelength of light is going to determine, what type of wave it is. If it's a visible wave, the wavelength will say, okay, this is an orange, this wave is orange. It's going to give us orange light. The intensity, how bright that orange is related to the amplitude. So if you have a lot of wavelengths put together, that amplitude is going to get really big, right? So in this case, I've just put two waves together, and we ended up with twice the amplitude. If I put 100 of these waves together, I'll get 100 times the amplitude. That's going to give us more intensity. All right, notice though that the wavelength does not change. The only thing that's actually changing here is the amplitude. So if we put 100 orange rays of light together, 100 orange photons, as we call them, those will still be orange when they combine into one wave. However, that orange will just be more intense in terms of how intense that light is. So we're going to see, of course, if you were to look at the sun versus looking at a light bulb, I do not recommend either one, by the way, you have a lot more photons coming out of the sun than you have coming out of a light bulb, right? And so the sun is going to be a much more intense source of energy than the light bulb will be. Okay, again, the wavelength is not going to change here, only the intensity will, and that's related to the amplitude. So notice also that because the wavelength does not change, the energy does not change. So you might be saying, like, what the heck? What's happening here? Like, the energy isn't changing. We saw that energy is related to wavelength, right? And so if the wavelength is not changing, our energy isn't changing. I know that seems bizarre. You can have really intense beam of light. The energy of each photon, though, does not change. Okay, so intensity can change. But the frequency and energy do not. Okay, so just understand the intensity of light, how bright it is not necessarily the same thing as its energy. Okay? Let's see what happens if we try and add up waves that are out of phase with each other. So here we go. Oh dear. Let me try that again. Okay, there we go. Drawing stuff is tough, guys. If these guys are out of phase, and that's really ugly, if we add those together, shouldn't have drawn that there, we're going to end up with a wave that looks like this. If these guys are perfectly out of phase with each other, as in they are, same wavelength and everything, and they're just completely out of phase, so when one of them is at its highest, the other is at its lowest, if we try to add those two waves together, we're going to end up with nothing. They have canceled each other out. And this is what's called destructive interference. So the light waves have in fact canceled each other out. And so, by the way, fun fact for you guys, sound is also a wave, right? It's not the same type of wave. It doesn't have a electromagnetic component. It's just a pressure wave, but it's still a wave. How your noise canceling headphones work is they will say, okay, that top wave is the sound coming in. And what they will do is they will take that sound and they will generate another sound. They will generate a sound that has the same wavelength, but it's out of phase. And so as a result, you will not hear anything, or it'll be a lot more muffled, right? Because those two waves will combine together and they'll cancel each other out. And so that's how noise canceling headphones work. They do the same idea here. They generate a wave that has the opposite phase of whatever waves are coming in. And so they continuously do this. So it's a pretty cool example of engineering here. Come on, Gumbo, you want to say hi to everyone? Alright, let's go get Gumbo. Okay. These guys are learning about light waves today. Gumbo says he doesn't care where are the treats. That's all he ever cares about, right? Okay. There's a reason we're doing all this stuff, by the way. I'm not just randomly talking about light for no reason. Do we have any questions on this stuff so far? Again, this is kind of conceptual. Yeah, right. Conceptual stuff is tougher to see problems with, if that makes sense. You're gonna like realize you have questions later, but right now it's like, okay, this stuff makes sense or whatever. So, but that's what Discord's for. Alrighty. Okay, so there is a point to all this stuff. So let's see what happens. Let's see what happens when light interacts with matter. And just what we're going to be talking about here is just atoms. So we probably remember, I'm going to just kind of draw what you guys may have seen before. This is what's called the Bohr model of an atom. It's one that's easy for us to kind of understand. We are going to learn another model that's a lot more kind of abstract, but you probably remember this, right? You have a nucleus, you have some rings outside which represent the orbitals, and you have electrons kind of occupying those rings. We're going to see that what can happen is here comes a light wave zapping that, and that can cause an electron to jump into a higher orbital. Light can cause an electron to jump to a higher orbital. So understanding all that's happening here, we are zapping our electron. The electron has absorbed that energy, and it'll just jump up a ring. Yeah, exactly. Depending on what the energy it is, it could jump up 2 rings or whatever. We won't worry about that. But just understanding that it's going to jump, right? It's going to move basically up into a higher level. This is, by the way, what's called a ground state. And this one is what's called an excited state. And the ground state just means that stuff had the lowest energy that it could have. And once we've zapped it with a light beam, it's going to jump up into an excited state, which has higher energy. Right? Remember, just like matter cannot be created or destroyed, energy can also not be created or destroyed. Right? So if we are going to give this atom some extra energy, that's going to be manifested in this kind of excited state idea. And what happens is, if you have, let me just draw these again. I know I'm just drawing crazy eyes. Let me just draw it first, and then I will. Okay, cool. What can happen is that excited electron in this excited state can drop back down into a lower energy state, and as a result, it will release a photon. It will release a wave of light. This is called emission. This one was called absorption. So if we absorb a photon, a wave of light, we can emit it back out again. Totally normal. And you're like, well, what's the point? Nothing's changed. I agree. Right now, nothing has changed. We will have other ways that we can talk about this. And notice, I was very careful to use the same color here. So what we're seeing here is we have the atom plus a photon, which is often a, let me just write that. Which is a photon is often abbreviated h nu. That just means a photon or a wave of light, a ray of light. This was our kind of excited state atom. And that atom can release that wave of light again. What's important to note is that this is the same energy as it was before. So if you blast your atom with a yellow beam of light, if it undergoes this process, it will spit out that very same yellow light of exactly the same energy. So that means it has same wavelength, same frequency, all that good stuff. You're probably like, what's the point? We're going to see that a lot of interesting other things can happen, where you might have an excited state atom maybe undergoing some other things that will cause it to lose a little bit of energy, and then it's going to spit out the rest as a photon, and that photon can actually have a different wavelength. That's called fluorescence. So sometimes, if we think about this vertically, electrons are often done with little arrows. Let me go ahead and draw that. And these are just kind of energy levels. So if we go ahead and if we blast it with our photon, we have our excited state one. Remember, this is exactly the same as we've done before. I'm just making it now with energy levels instead of those orbitals. Same idea. This was our ground state here. We have given it some energy with a photon. It is now an excited state. What could happen, again, it could just release it all. Let me draw that for you. It could release it all plus the same energy. Or, oh goodness gracious. Okay, let me just use a different color, sorry. So we have our excited state. What could happen is it decides, okay, I'm going to actually like wiggle around a bit. I'm going to use some of this energy to rotate or vibrate or do some other, something that's going to deplete our energy. This could be rotation, vibration, some sort of way that we're going to use that energy, right? So, we can do that. So we're now going to move to a slightly lower energy state. And now we can blast that down to its other one. But in this case, this photon that's released is lower energy. So remember, I'm sorry to have to keep scrolling up on this. We put in a certain amount of energy. Let's say it's, I don't know, 100 electron volts or something. Or you know what? Let's just say it's purple light. Okay, this one would be purple light again, because it's just releasing the same amount of energy that came into it. However, in this second case, where we have lost a little bit of energy to rotation or vibration or some other process, we're going to see that now this one might be a green photon that comes out. So we put in purple light. The atom did some sort of energy losing process. And when that electron relaxed back down again to the ground state, it released a lower energy photon. This is what is called, goodness gracious, oh, don't need contacts. This is what is called fluorescence. So that's what happens when an excited loses a little energy to rotation or vibration or whatever, some other way of it to use its energy up, and then releases a photon with lower energy than the absorbed photon. So remember, to get into an excited state, we have to absorb a photon. We have to get that light wave in, right? When we do this fluorescence thing, we can lose a little bit to rotation or vibration, and then we can spit out a absorbed photon, spit out a different photon that has a lower energy than the one that we absorbed. So again, just some definitions for you guys. I'm not going to be asking you to calculate anything like this, but just some definitions of what's happening here. Okay, any questions on that so far? It's just a process. So when it jumps up a ring that could do other things, to when it comes back down, I have lower energy than it did before. Cool. Okay, so in that case, let me see. While you guys are potentially writing questions, I should pull this up. I'm going to show you something from our textbook. Just in case some of you don't have it, I want to show you one of the videos that we have here. And I know that when I type on this particular laptop, it's super loud in the microphone. Apologize. It's just going to like be loud. Okay, cool. So with this here, I want to show you a video of the point of all this crap. Let's see, we are on chapter 4. Okay. Let's see the point of all this fun stuff. Can we use mic and Twitch? Like, you want to talk? I can make it that way. If you want to talk in Twitch, go to the classroom that we're in. I can turn on the audio sounds. Yeah, of course. So in that case, let me just turn on desktop audio. Okay, so if you want to say something, go in Discord and just go into our kind of classroom channel. And go ahead and do that. And then once you're in there, you're going to be able to chat with us if you want. So, do you know where to go for that? I'm here with Daniel, and so you should be able to see us there. Okay. Well, while you're doing that, I'm going to find this silly video. Again, I should have done this earlier. Aha! Okay. So let me just now. This happen. Video capture. Oh. Okay. Cool. Hooray. So here is.
We've dissolved various salts into water and heated them up to excite their electrons. As their electrons fall back to the nucleus, they're emitting different colors of light. Here we have lithium salt that's emitting a red color, sodium salt giving out a yellow color, copper with a nice green color, and finally a cesium that has a purple color.
Okay, cool. Burning things, fun, right? So, let's close that window capture. Okay, the point of that is we're going to see that every atom has specific wavelengths it can absorb or emit. So, by the way, that yeah, this is exactly how fireworks have different colors. Woohoo, fireworks. And this is also why, for example, like if you think about fire, most fire is kind of that orangey yellow, right? In real life, like if you were to burn wood or something, that's because the wood has a sodium in it, and the sodium is what gives it that kind of yellow-orange color when you burn it. You'll probably notice that on your stove, you don't have that color, right? You just have normal blue fire on your stove because there's not any sodium in there. However, if you wanted to, have your stove going and sprinkle some salt or some baking soda on it, you'll see that it will turn that kind of yellow or orange color. Because that sodium that's in that has very specific what are called emission spectrum lines. So what this means is because wavelength is related, let's say not related, let's say proportional to energy, each atom has specific energy levels. Oh my goodness. Energy levels. And that means, for example, just kind of like random ones. Let's say this is sodium and this is potassium or something. This is one ground state. We're going to see that this energy difference between them is not the same. So when we excite these atoms, these electrons, and they fall back down again, these are going to have different wavelengths, which are going to mean they have different colors. And different energies. We have fancy words for all this stuff. We say that these energy levels are quantized. And that means there are very specific or what we call discrete energy levels. I know that I keep saying energy levels and you guys have like no idea what I'm talking about. So if we kind of go back to our Bohr model of the atom where we had nucleus and all these rings around it, the spacing between those rings is different for every atom. That's what I mean to say. So, like, for example, a sodium and a potassium atom will have different spacing between those rings. And because we can only absorb very specific wavelengths of light, so that corresponds to the energy level between those two. So if you get, this means a photon, oh my goodness, that's just an H. Oh, I can make that work. Photon of incorrect color cannot be absorbed by a particular atom. Because these have very specific energy level differences, again, the difference between a ground state and an excited state is different for every atom, like E1, E2, let's say. A sodium atom will only be able to absorb photons that have the energy that's exactly equal to E1. And a potassium atom will only be able to absorb an energy, a photon of energy equal to E2. So, specific things. These guys can only absorb specific energies. And so that's why these things are going to have different colors when they release them, is because these are very specific levels. Of course, there's more than one excited state per atom. You don't just have one energy level in sodium. You're going to have a whole bunch of them, but they're very specific. Okay, so one particular, wave will come out if you were to give it a particular wave. I know I'm just saying wave all the time in energy levels, and it's all getting very confusing. No worries. Sleep on it at 10 a.m. Go ahead and take a nap. We'll continue this tomorrow, and we'll start talking about more stuff with electrons. Okay, so I know we're running a tad bit late here, so just so you guys know, on Thursday we're going to do an exam review, meaning we're going to go over... Correct. You can never release a higher energy than was put in. You can release a lower energy, but never a higher one. That is not a stupid question. That is a very important one, actually. So that is a very good point. Yeah. So Thursday, exam review. If you want to show up, we'll say, can you go over this particular question? Just so you guys know, you did have somewhat different exams, meaning that I had pools of questions and it would kind of randomly pull different questions. So you guys may not have exactly the same exam as each other, but they should be of similar, like I put in, 5 questions on molds or whatever. It's going to pull from a pack of 10 questions of similar difficulty. So it's not like unfair like that, but when you are going to be asking those exam questions, if you want me to go over certain ones, I'm going to ask you to maybe take a screenshot or something of the question and post it in Discord on Thursday so that I'm able to see and your fellow classmates are able to see what question you have. Because your question 5 may be very different from someone else's question 5. So, yeah, cool. Okay, so I will see you guys tomorrow. We'll continue talking about electrons. I'll give you some homework as always. And then Thursday, if you want to show up, we will have our exam review that day. Okay, cool. See you guys tomorrow.